Hello, my name is GRV.SRIRAM. I am from CSC Data Science Department. My roll number is 24951 A6747. The course title of this presentation is Probability and Statistics, and the topic title is the Central Limit Theorem for Functionals of Markov Random Fields. The Central Limit Theorem for Functionals of Markov Random Fields. Unveiling the power of central limit theorem in complex spatial systems. What is Markov random field? MRF. An MRF is a graphical model that elegantly represents joint probability distributions using an undirected graph. In this graph, nodes signify random variables and edges denote the conditional independence relationships between various variables. A cornerstone property is the local Markov property, and in each node it becomes conditionally independent of all other nodes in the graph. So the given the state of its immediate neighbors, a cornerstone property is the local Markov property, in which each node becomes conditionally independent of all other nodes where they are present in the graph and given the state of its immediate neighbors. From Markov chains to the Markov random fields, Markov chains, MRF generalization, functionals of MRFs, crucial for inference. First, the Markov chains. Markov chains are the sequential processes where the future depends only on the present, not on the past. So the fundamental in it is the fundamental in sto- stochastic modeling. And the second one is MRF generation. MRF Markov random fields generation. Extend Markov chains to multi-dimensional grids or graphs, capturing complex spatial dependencies rather than just temporal ones. Here, the third one is functionals of MRFs. Functionals of Markov random fields often involve aggregate measures such as sums or integrals across local configurations or states within the field. Crucial for inference. Understanding the limit behavior of these functionals is vital for robust statistical inference and accurate scientific modeling. The classical central limit theorem, CLT recap. The classical central limit theorem is cornerstone of probability theory. It states that for a sufficiently large sample size, it's always the sum or average of independent and identically distributed IID random variables when appropriately scaled will converge in distribution to a Gaussian normal distribution. So the variance of the individual random variables is crucial. It dictates the scaling factor and ultimately the width and shape of the limiting Gaussian distribution. However, in contexts involving dependent data such as Markov chains or Markov random fields, these dependencies significantly complicate the straightforward application of classical CLT, affecting both the variance structure and conditions given for the convergence. Markov chain central limit theorem CLT. For additive functionals of ergodic Markov chains, a central limit theorem holds under specific mixing conditions. The variance of the limiting distribution, denoted by sigma square, needs to account for serial dependence. And here the formula is sigma square is equal to var of f of x naught plus 2 into sigma k is equal to 1 to infinity how of f of x naught comma f of x of k. This formula highlights that variance is not merely the sum of individual variances, but includes critical convariance terms reflecting the influence of past states. For instance, consider the hardcore model on a grid where particles cannot occupy adjacent sites, but Markov chain Monte Carlo MC methods can simple valid configurations forming an ergodic Markov chain. The CLT then allows us to estimate the expected number of occupied sites, a functional with quantified confidence, despite the strong spatial dependencies. Extending CLT to functionals of MRF. CLT Markov chain central limit theorem to Markov random fields. Challenges of MRFs. Unlike Markov chains, MRF exhibit more intricate spatial dependencies across multiple dimensions, making their analysis considerably more complex. Functionals of MRF typically involve sums over local functions of node states or configurations within clicks. To establish a central limit theorem for these functionals, two critical conditions must be met: the existence of a finite, invariant, and ergodic measure for the underlying MRF, demonstrable strong mixing or sufficiently rapid decay of colorations, either spatially or temporally. These conditions are paramount for ensuring that Gaussian fluctuations Gaussian fluctuations emerge in the large scale limit, allowing for robust statistical inference even in high dependent spatial systems. Key theoretical results and conditions. Pioneering work. Seminal contributions from Cockburn 1972 and Gordon and Lefesik 1978 laid the groundwork for CLTs in Markov processes and fields, setting the stage for future developments. Jones 2005 provided crucial insights into conditions linking drift, mixing, and ergodicity for CLT validity in general state spaces, unifying disparate results. Mixing conditions. These are vital. They ensure that the dependencies between random variables weaken sufficiently rapidly, whether over space or time, allowing for a return to statistical independence. Ergodicity guarantees that time averages converge to ensemble averages, providing long run statistical regularity essential for asymptotic theorems like CLT. Practical implications and applications. Statistical physics. Essential for understanding phase transitions and thermodynamic fluctuations in lattice models, such as Ising model, where interactions are local but have global effects. Spatial statistics. Applied in geoscience and epidemiology to estimate means and variances of spatially dependent data, enabling robust predictions and risk assessments. Image analysis. MRFs are widely used for texture modeling, image segmentation, and noise reduction. The CLT provides Guardian Gaussian approximations for inference, which are crucial for complex visual data. Markov chain Monte Carlo (MCMC). The CLT is fundamental for accessing the convergence of MCMC algorithms and for estimating the variance of sample means from dependent MCMC outputs. Critical for Bayesian inference. Visualizing the CLT for MRF functionals. Observe a grid of nodes, each colored black or white, representing a specific MRF configuration. As we compute the local sum of local functionals, example, the count of white nodes across increasingly larger grids and normalize these sums, their empirical distribution will progressively approach the characteristic bell curve of Gaussian distribution. This dynamic illustrates the emergence of central limit theorem in action, even within the complex spatial dependencies of an MRF. Conclusion. Why the CLT for MRF functionals? First one, rigorous foundation. Provides a robust framework for conducting statistical inference on complex spatial models, quantifying uncertainty with precision. Uncertainty quantification enables accurate measurement of uncertainty ethics, where data points are inherently dependent, crucial for reliable decision making. Bridging disciplines connects theoretical advancements in probability with practical applications across diverse fields, from statistical physics to cutting edge machine learning and future research. Ongoing efforts aim to explore weaker conditions for CLT validity and broaden its applicability to even wider classes of functionals, pushing the boundaries of statistical understanding. Thank you.